Part 6 named a real limitation plainly, which is that every model has a knowledge cutoff, and past that point it will still answer confidently, but it just won't be right anymore. The model doesn't have knowledge beyond the cutoff date. This video is about the most common fix for that problem. This entails making a model check a knowledge base before it answers. That's called Retrieval-Augmented Generation, or RAG, and this video maps how it works. That's called Retrieval-Augmented Generation, or RAG, and this video maps how it works. Welcome back to the Artificial Intelligence Institute Africa, AIIA, pronounced Aiia. Ubuntu Guild videos on AI. I'm Dr. Denis Magaya, Chairman Aiia. This is part 14, Retrieval-Augmented Generation. How a model is given fresh, specific facts at the exact moment it needs them. Recall from part 12, a model's knowledge is frozen at the point its training data was gathered, and beyond that point it will still produce a fluent, confident answer, just not necessarily a correct one. Retrieval-Augmented Generation attaches a search step in front of the model. Before it answers, relevant documents are fetched from an outside source and placed directly into its context, and only then does it generate a reply. The model isn't retrained and doesn't know anything new permanently. It's simply handed the right material at the right moment, the way a well-prepared advisor is handed today's briefing before walking into a meeting rather than speaking from memory alone. That outside source doesn't have to be the public internet. It can be a private database with internal policies, documents, or product manuals. Most organizations actually use RAG exactly this way, to answer questions from their own private data, without that data ever training the model or leaving their own systems. In simple words, RAG doesn't make a model smarter, it makes sure the model isn't answering blind. Part 6 introduced 3 ways to adapt a model: prompting, RAG, and fine-tuning, and it's worth being precise about where RAG sits. Fine-tuning changes the model itself, real further training at real cost that has to be redone whenever the underlying model updates. RAG changes nothing about the model. It changes what the model can see. The same way handing an elder a fresh written report right before they speak doesn't retrain the elder. It just puts today's specific facts in front of them for today's specific question. That distinction decides which one solves your problem. If the issue is that the model doesn't know something, a fact, a document, a number that changes weekly, that's a knowledge gap, and RAG solves it directly. If the issue is that the model knows the facts but answers in the wrong tone, format, or style, no amount of retrieval fixes that. That's a behavior gap, and only fine-tuning reaches it. In simple words, fine-tuning changes what the model is. RAG changes what it's looking at in the moment. Part 13 described an agent as a loop that calls on specialists to get a job done. On tools such as the web, another queries a database. Retrieval is exactly that kind of specialist. A RAG pipeline on its own only ever does one thing: given a question, fetch relevant material and answer once. An agent can call that same retrieval step as one tool among several mid-task, deciding for itself when a question needs a lookup and when it doesn't. Think of it like this: a basic RAG system looks something up once and just answers with whatever it found, even if that's not quite enough. But when RAG is built into an agent, it works differently. If the agent realizes partway through a task that it's missing something, it goes and looks it up again right then, as many times as it needs to. It doesn't just guess or give up. It goes and looks it up again right then, as many times as it needs to. How a pile of documents gets turned into something a computer can search by meaning. Layer 2 is retrieval, how the right passage gets found among thousands of candidates. Layer 3 is augmentation and generation, how that found passage reaches the model and what the model does with it. And layer 4 is what breaks the specific common ways a RAG system fails, even when every individual piece looks like it's working. Layer 1 is your foundation. Layers 2 through 4 build on top of it, one at a time. Let's start with layer 1. Let's start with explaining chunking and embedding. Before anything can be retrieved, a large pile of documents has to be broken into pieces small enough to search. A process called chunking. A whole report is too large and unfocused to hand a model as one piece. It gets split into passages, usually somewhere in the range of 200 to 500 words at a time, often with a little overlap between neighboring chunks, so an idea that spans a chunk boundary doesn't get cut apart entirely. Then each chunk gets converted into an embedding, a list of numbers that captures its meaning as a position in space, the same idea introduced back in part 1. Think of a spice trader's stall where the jars aren't arranged alphabetically, but by scent. Cinnamon sits near clove, not near coriander, because that's what matters when someone's looking for something similar. An embedding does the same thing to a passage of text. Chunks that mean similar things end up sitting near each other in that space, regardless of which exact words they use. In plain words, chunking breaks a library into passages small enough to search. Embeddings arrange those passages by what they mean, not by which words they happen to contain. Now let's talk about retrieval. Think of a messenger sent into a vast archive to fetch precedent for a case the judge is about to rule on. The messenger doesn't bring back the whole archive. They bring back the handful of scrolls that bear on this specific question, judged by how closely each one's subject matches what was asked. Retrieval has 2 steps mechanically. First, the question itself gets converted into an embedding using the same method as the chunks. This is what makes it comparable at all. Second, that embedding is compared against every chunk's position in that space, usually with a calculation called cosine similarity. Similarity equals A.B over norm A norm, norm B norm, which measures how closely 2 embeddings point in the same direction, regardless of length. The handful of chunks with the highest similarity score, typically the top 3 to 5, often called the top K results, are the ones retrieved. Tools built specifically to do this search quickly across millions of chunks, such as FAISS, released by Meta AI in 2017, are what make this practical at real scale. 2 refinements to that search process are close to standard in real systems now. Similarity search alone can miss an exact term. An embedding might blur a specific drug name or product code into something merely similar, when the question needs that exact match. Hybrid search fixes this by running a traditional keyword search alongside the similarity search and combining both rankings, so an exact term isn't lost just because it wasn't semantically distinctive. And because that first similarity pass has to run fast across millions of chunks, its ranking is only approximate. A second, slower step called re-ranking takes the top candidates from that pass and scores them again, more carefully, before the final few are chosen. Production systems increasingly run both, a fast, broad first pass, then a slower, precise second pass over just the survivors. In plain words, retrieval turns the question into the same kind of number. The chunks were turned into and hands back whichever chunks sit closest to it, often refined by a keyword check and a second, closer look before the final few are chosen. Now let's turn to augmentation and generation. This is the step that gives the technique its name. The retrieved chunks aren't just found, they're inserted directly into the model's prompt ahead of the actual question, the same way that Elder is handed the report and reads it before opening their mouth. The model then generates its answer the exact way part 6 described, 1 token at a time, except now its context includes real, specific material it never saw during training, sitting right alongside the question. This is also where the approach was first formalized as a single technique rather than an ad hoc trick. In a 2020 paper from Meta AI, a retrieval-augmented generation for knowledge-intensive NLP tasks, which showed that pairing a retriever with a generator this way measurably reduced exactly the kind of confident wrongness called hallucination. Say it back in plain words. Augmentation is placing the found material directly in front of the model. Generation is the model answering with that material in view, not from memory alone. Layer 4, what actually breaks? A RAG system can have a perfectly good model and still fail in a few specific, well-documented ways. If retrieval brings back the wrong passages, the model answers fluently and confidently from material that was never relevant. The model isn't broken. The messenger simply brought back the wrong scrolls, and everything built on top inherits the mistake. Chunk size is a real trade-off, not a solved setting. and a chunk loses the surrounding context that gave it meaning. A sentence about the treatment with no record of which disease it was treating. Cut them too long, and the one genuinely relevant line gets diluted inside paragraphs of irrelevant material and costs more tokens besides. And even once the right material is retrieved and placed in the prompt, where it sits matters. Research specifically measuring this, lost in the middle, how language models use long contexts, found that models are measurably more likely to use information placed at the very start or end of a long context and more likely to overlook something buried in the middle. The same way an official skimming a long stack of papers reads the first page and the last closely, and glances past whatever's buried in between. There's also a slower failure that's easy to miss because nothing looks wrong on any single day. Documents change, a bulletin gets revised, a policy gets updated, but the embedded copy doesn't update itself. Unless something actively re-embeds the changed document, the system keeps confidently retrieving a stale version long after the real one moved on. The same way a messenger who hasn't visited the archive in months keeps handing over precedent that was quietly overturned. And if the embedding model itself is ever swapped for a newer one, every chunk embedded with the old model has to be re-embedded to stay comparable. Mixing embeddings from two different models in one index still returns a similarity score, just a meaningless one, and it fails silently rather than with an obvious error. In plain words, a RAG system can retrieve the right document, chunk it sensibly, and still fail quietly. Because where a fact sits in the prompt changes whether the model notices it. That's chunking, retrieval, augmentation, and generation, and the specific ways a RAG system breaks, the 4 layers laid out plainly. Everything covered in this lesson explains how RAG works and where it quietly fails. In the next lesson, The Explained, we'll watch a real RAG system run through a worked example, and then walk through the concrete steps to build one yourself. Thank you for watching this Artificial Intelligence Institute Africa AIIA video brought to you by Ubuntu Guild. Subscribe to our AIIA YouTube channel and to Cognify, and join us for the next lesson.